I think we have past the start, so then I would like to welcome all of you attendees to this webinar. TECHNIA is organizing webinars, and we have had quite a few on different topics this year. And today the topic is we have invited a guest speaker from our customer in Norway, Kongsberg Defence and Aerospace, which is a long-term good customer of TECHNIA in the air, in the domain of both Enova and CATIA, and for a couple of 3-4 years actually we've been looking into the area of systems engineering together with Kongsberg, using the Enova and the CATIA solutions. And we are very fortunate today that Gudrun Straand, Mrs. Gudrun Straand, is joining us to talk about this, how they have been using the solution and some of the experiences so far. So if you are ready, Gudrun, I will give you the hand.
See my presentation now?
Yes, I can see this loud and very good.
Perfect. So I work in Kongsberg, and today I will talk about the Local Hawk project and how we do model-based systems engineering in that project. First, an introduction about Local Hawk, and then I will go more deeply into the model-based systems engineering and model-based systems engineering in CATIA. First of all, I want to show you a little film from the Local Hawk project this year.
Så lenge det kan. Nå er flyet ferdig. I dag skal vi først teste at alt fungerer slik som det skal. Og så skal vi vise det frem, vi skal demonstrere det for hele missildivisjonen. Når vi står med propellene opp sånn her, så er det jo løftekraften egentlig bare bestemt av hvor fort de her spinner. Men så fort vi begynner å tilte de her frem, så er det vingene som gir oss løftet til å holde oss oppe. Så vi er usikre på om vi får nok fart fremover, eller skal vi si luftstrøm over vingene, for å få nok løft her til å holde oss oppe.
So, this was a sneak peek of the project, so now I will continue with the slides here. So, this is a project in the division missiles. It was established in 2008, and it has been growing every year. And last year we had 23 students working to develop a drone. And the thing is to develop an UAV that can identify and film cars competing in a folk race. And a folk race is especially known in Norway and Sweden. Here you see the cars. It's quite cheap cars. And our plan is to follow the car during the race, and you can film one particular car. Even if it crashes or drive out of the raceway, you shall be able to film it. So this is the racetrack. You can see that the cars are holding quite high speed at the straight end of the race, and in the curves they are slowing down, of course. So there are a few, it can be a bit difficult to be able to film it, but that's the task for the students. So the technical solutions in the project are based on our own expertise here in Division Missiles. that will say that we have systems engineer, we have image processing, mechanics, electronics, software development, guidance, navigation and control, and we have supervisors supporting the students, and we have a project manager. So this student project is reflecting a real development project. So the purpose of the project is to recruit the best students. It is to test new technologies and processes, like this model-based systems engineering, and of course to gain publicity and to get a strong brand among students, and show that we are responsible in motivating students for engineering studies. And the students, they will get knowledge and know-how that they don't get at school. They will try how it is to work like a real engineer. And of course, the student, they come right from school with fresh ideas and innovative thinking, so it's a win-win situation for all. So what's the link between missiles and local hawk? Many people ask, why should you develop just an airplane, an RC plane or a quadcopter you can just buy from a shelf? It's because the local hawk project is actually quite similar to missile development. They are both complex systems with all the different subjects that I showed you, and the main technological topics are almost the same, like aerodynamics, autopilot development, etc. And they are, of course, both knowledge-based development. It is because of the knowledge that we can be able to develop the local hawk within only 7 weeks. So the differences are, of course, time span. Local hawk project lasts for 7 weeks during a summer, while missile development takes decades. And when it comes to resources, in the local hawk project we have 23 students, but in the missile division it works about 400 to 500 people. And local hawk is non-commercial and not military classified. So that is the reason why we can have students working on the local hawk project, but we cannot have students working on the military graded projects. So therefore we can also present this project to people like you and describe a little bit how we work through the local hawk project. And the challenges are the same, or many of the challenges are the same between local hawk and missile development. How can we be able to do the right things at the right time, to finish at a given date? When the students start working in June, they know that they will have a test flight in August, and at that time it shall be a completely working prototype. It shall up in the air flying. And how can we transfer knowledge across disciplines? When the students come here to work, they come from different disciplines at school. Some are software students, others are mechanical designers, and they shall understand each other to be able to make a complete system. And how can we make essential documentation and know-how easy accessible from year to year? It's like when the students come here in June, they cannot be able to read through all the material the students last year made. That will take too long time. So they need to find information and the essential information and be able to get know to it in a very short time. And how can we let engineer do engineering and not do a lot of documentation that they believe is unnecessary? That's the main challenges. And to overcome the challenges, we have put an organization with 23 students, about 3 to 4 students per group, with both theoretical and practical skills. We have the brightest minds and people with who are both theoretical good and people who have been having a lot of practical experience. And we are organized with a steering committee from the division, and we are having a project manager for this project. I was a project manager last year, and about 10 tutors, 1 to 2 tutors per group. And 6 of the students from this year's local hawk were also participating last year to ensure continuity. And we have a student project manager for daily follow-up. And as CATIA said, in cooperation with Dassault and TECNIA, 2 years ago, we started having system architects to see the overall picture and to be sure that people are cooperating well and they can see the links between the different disciplines. And when it comes to work processes, we have the model-based systems engineering and lean product development. We use visual project boards for planning, and we have short stand-up meetings, so we can plan almost from day to day so that everything will be on time. And we have A3 documentation for information storage, and that information will be stored in an RFLP model in CATIA. I will tell you what that means. It's a model-based system structure where we store models and visualize the documentation rather than have long written reports. And of course, the way to success is rapidly testing in this project. So then I will go over to the model-based systems engineering. RFLP stands for requirements, functional view, logical view, and physical view. So what is that, you might say? To define a view in general, we can say you're going to build a house, and in the middle, this is your vision about the house. And then we see that to build a house, you need different specialists, and they need different kind of information. The architect needs information from you about how you want your house to look. The bricklayer needs information about the ground conditions, etc. And the electrician are going to put up the light bulbs, the wires and the fuses, etc. And they all need different kinds of information to be able to build the house you want. So you can say that people look at things differently and they need different kinds of information. They see things in different views, like we engineers do in a development project. So the RFLP can we also put in our development process. First we have the customer who comes with a need, and then we have to define the stakeholder requirements and analyze the requirements. Then we make up a logical design, which is the same as conceptual elements, where you have not defined the exact shape or type or kind of product or component, but it's an idea of a kind of component or product or part. And then we do functional decomposition of the product or the system, and then we do the loop once again until we find it implementable, and then we have a physical product that we can integrate, verify, validate, and deliver to the customer. So then we have the RFLP also in the product development process. And translated into a RFLP model and local hawk, we can have this image where we have requirements, we have a functional view, logical view, and a physical view. That's what we see in the CATIA model, as I will show you. And we also have the behavior. That's something we think is important. It's how the customer describes his needs and how he wants the system to operate. And that's the foundation for the requirement and the functional decomposition and the logical decomposition. And then we have our A3 documents linked to the different views, so it shall be easy to find, rather compared to a Windows Explorer where you store the documents. Here you can find it by looking at a visual figure. If you're wanting information about the wing design, you can either look into a function which said generate lift, or you can look at the physical view and click on a wing and find the information. So if we go into the model, here we see the top level of the logical view. It's what the customer wants. We see a system consists of a car race, an operator, ground station, a UAV, and support equipment. In the CATIA model, we also see in the navigator tree, we see a requirements layer, functional, logical, and a physical layer, where we can switch among the different views. And in the background, you see different designs, the physical views. These are different 3D models of the Local Hawk drone from 2012, last year, and this year. As you see here, you can look at the left top of the slide where it's indicated if you are in the RFLP, the requirement, functional, logical, or physical part of the system. First of all, we have the concept behavior. That's the consumer's needs and wants. It describes how he will the system to operate. He wants to transport the UAV into a car, unload it, prepare it, launch it. He wants to fly it, operate the camera. When he lands, he wants to extract the data from the payload, then process the recorded data, etc. And when it crashes, of course, then there's a flight error. Then he wants to transport it back to the UAV. So this is a kind of way to visualize the wants from the customer. You can use it for the marketing, people can use it, and all the different engineering disciplines can look at it and see if they have understood what you should do. And from this we extract the requirements. So the top function in this case is to capture video of a race car. If we zoom in, we can see that there's input information, race map, race information, real-time UAV observation, there's human interaction, etc. And the output shall be UAV movement and video for processing. We use pictograms for these functional parts of the model, while for the logical parts we use hand-drawn sketches. So this is the top function, and here allocated to the top function we see all the top requirements, the titles of the requirements, like speed of race card, launch time, picture transmission frequency, etc. So this is the icon you shall look at after if you are looking for different requirements. Then at top level we have added an A3. This is an example of an A3. It's an easy way to understand the documentation. It's not a written report about the different concepts. It's some pictures and a matrix which consists of the top requirements here. And we have been choosing to use a vertical takeoff and landing aeroplane for this drone, for this system. When the top function is to film cars during a folk race, and we know that the cars, they can stop, they can crash, they drive fast, they drive slow, and there's not an airplane strip there. So we are making a solution with vertical takeoff and landing. It's a hybrid between a multicopter and a plane, so that we can take off vertically and then fly horizontally, and we can hover over the cars if they stand still, if they've been driving out of the track, etc. So this is an example of an A3 documentation sheet. So if you're going to the logical view, top level, the logical view of the UAV, we see what parts the UAV shall be built up of, like an airframe, flight computer, power, thruster system, that's the propellers, car tracking system, etc., servos. And here the yellow lines are the electrical connections, the blue are the mechanical interfaces, and the red are sensor signals. It makes it easy to understand what it shall be built up of. Especially for the mechanical designers, it's very good to see actually what's going inside it. You can see that could be a lot of cables, and the sensors and computers actually could take up a little space. As we experienced this year, cables takes a lot of space, so we had to build a box on top of the fuselage actually. So this is before we have decided what kind of fuselage, what kind of computer, what kind of power. It's the concept, the logical view. So if you go down to the functional view, it's the functional view and the sub-function of capture video. We see here we have to fly the UAV, we have to track car, we have to record footage, process video, and control UAV. And in between we have defined all the signals or all the information that shall go from one function to another. That's a good way to make sure the engineers will have the same meaning of the system, and that they are designing the right thing when they start doing detailed design. So if we go into track car subfunction, it's further decomposed into a new function. Here we use image processing for recognizing the different cars. We are going to put a symbol, a circle, on top of the roof of the cars, and then we have to film the cars by the camera, and we have a template in the computer, on flight computer, and if there's a match with the filmed car, it will send the target position to the computer. So I will show you just how it works so you can get a glimpse of it. Here's no sound because we haven't put music or something into it, so you don't need to bother about that. Here you see the icon that shall be on top of the car, and here's a square. That means match, and the camera is following the image here, and here's the GPS coordinates. And when they jump behind the cars, it said target not match, target not found, sorry. So that's how we recognize the cars, but then we need to stabilize the camera. This summer we just tested it on ground, but next year we have to get the camera up in the air, and because of the vibration during flight, we need to stabilize the camera, and here's another function for that in the track car subfunction. So here's the stabilize and point camera. We need to adjust the camera in all directions, yaw, pitch and roll in X, Y and Z, and measure the orientation, and the output is the camera orientation. So here in the bottom of the architecture, we see that there's a link to the logical architecture, and here is a link to the physical model. I will show you both. This is the logical view of camera gimbal concept. Here the students did not have time to make all drawings, but you see it shall consist of gimbal motor in yaw, pitch and roll axis. We shall have dampening. It should be mounted to the fuselage. We're going to have an inertial measurement unit, and here you see the different kind of connections, mechanical interfaces and sensor signals. For mechanics, you can see here the bolts, and here's the power and the orientation. And here is the final 3D model that was designed this summer, and we also have here a demonstration of it. We built it also. Here you can see without stabilizer the image is shaking a lot. And when we put on the stabilizer, the image is quite still, so it works. And it was actually because of the system architects in our group that we found out we must to have a camera stabilizer, a gimbal, and a different camera than we believed we should have. Because the system students, they were having the overall picture, and they were able to see the links between the image processing group, the mechanical groups, and to see that here's a missing link, and that's the camera gimbal, and we need a new camera. So it has a very important function to have system architects doing system work. So if I want to show you more about this physical 3D, the design of the fuselage or the total airplane, I'll go back to the second level of the top function, the capture video folk race. Here with, the flight UAV, track car, process video, record footage, etc. So here I go down to the fly the UAV, and we see that there's some requirements allocated to fly the UAV that will say requirements concerning the aerodynamics and the mechanical shape of the wings and aeroplane. And then we right click on the function. We right click here on the function, and up comes the documentation that is allocated to that particular function. And here are the concepts for an A3 showing the vertical takeoff and landing concepts. We have this summer the students were, based on their requirements and the functional decomposition, they were designing different kinds of VTOL concepts. And then we made two prototype. One prototype with the winning concept here. It's a tilt rotor plane, which you saw in the film, where the rotors are tilting when you're going to fly forward. And here are the 3D design. Here are the rotors that shall be tilting forwards or upwards if you want to operate like a quadcopter or an aeroplane. And here's another concept designed this year with wings in the fan and a rotor which is tiltable at the tail. And these are showing last year's concepts and concepts from 2012. And by storing these concepts of the drones, then we can see, okay, they rejected that design, and then why did they do it? Then you can go in and look at the A3s, and then you don't want to do the same mistake again. You can, the goal with the model-based design is that you shall store your information during the design phases. You're going to write a short A3 during the design phase and the development phases and upload it easy during your work rather than wait until the end and write a long written report. So then it will be easier for the ones that come the next year or the other disciplines during your design, that they can find exactly the information they need. You know, if we go back here, they can go into exactly what kind of function they want and find information. They can find, okay, you designed it this way. Why is that? Is that because the requirements told you to do so? So it's a kind of good way of communicating between disciplines. So to sum it up, we can say that this model-based design is alive and it's dynamic. You can easily change one part of it without having to redesign all of it. And you can and it's always in change. It's dynamic, so it's nothing you just are finished with this date or another date. It follows during the entire development life cycle. So if you quit, the next person who's going to take over your tasks, he will find your work quite easily and I think it will be easier to take over your role or your work. So it will improve the communication across functions and levels between different kinds of engineers. It will be easier to confirm that you are talking about the same thing, and it will be easier to communicate. And between levels, marketing people can understand it. The sales people can use the behavior description to confirm with the customer that this is really what he or she wants. And with using this model-based structure, we think that engineers would use time on development rather than documentation. They shall document easy and, don't use a lot of time of writing reports, just the essential part of their work shall be documented on an A3 and uploaded into the model. And of course, you get easy access to relevant knowledge and information. That is very important in the local Hawk project when we have only 7 weeks of development. Then the students will find the information quite easy. Instead of having to look in a long report after one little thing, they can just go straight into, is it a computer or is it the autopilot they are interested in? They find the information they need just right there. So therefore it will increase efficiency. We think people will do the things they shall whenever they shall do it, and do the right things at the right time. And then it will, of course, then reduce the costs in the development projects because all the work we do before we start building and development, we are using a lot of time on the requirements, the functional decomposition, and the logical concepts, rather than just start making the first study advanced. So using a little bit more time in the early phases of the project will reduce the costs. So, do you have some questions? Or was it something I said that was not so easy to understand? Just tell me.
Yes, thank you very much, Gudrun. This is Ketil then again. Can you hear me?
Yes.
Yes. Now, what I will try to do is to unmute everybody. Before I do that, please bear in mind that you will be online, all of you, at the same time.
Yeah.
So from Henry Syrjalainen, he's questioning, how about system usability? Was it easy to learn how to use CATIA RFLP?
The students, they took it quite easy. And I think that especially we didn't use it this year, but the 2014 version of CATIA, I think it has a very good usability.
Yes.
The students, they took it good. Of course, the system students, they were here 2 weeks in beforehand to learn how to work with it.
Okay. So for all of you guys, Kongsberg KDA has been working on the 13X for some time, 2 years. They are running 2 environments, one environment for the local Hawk, and actually in parallel they are also running an industrial version on the 14X. So KDA is validating both the solutions at this time. And moving forward, the comment would be that the target would be working on 14X. So usability is improving. I have another question from Lars Hansen. How much work did you have to do on CATIA and Enovia to have RFLP working? Tricky question.
That was exactly not my part or the students' part. That was done by the IT department here, or Gerove, you know. So I guess Ketil has a better answer.
I think Lars Hansen. I think it's 2 different aspects. It's the infrastructure, installing everything IT-wise is some issues.
Yeah.
It's quite plain straightforward actually. It has been working very nice. The other aspect is how you implement and start using it as a user, and this is what you communicate. The students is actually up and running in a couple of weeks.
Yeah, and that was for the students who had never been into CATIA. They were in there very fast, and yeah, it didn't take a lot of time. Of course, the students, they are used to use different kinds of programs, and they have been learning at school to use a lot of different software, so I think it's quite easy for them to switch among tools rather than maybe people who have been using the same CAD system for 10 years, of course.
10 years? Even more.
Even more, yeah.
I think it's a good comment, and the new generation are adapting very fast. But I think it's going from CATIA V5 to V6 is some change, but I think it's more in thinking in different levels. Thinking in R, thinking in F and L and P is a bigger challenge, I guess.
Yeah, and the layout of the new CATIA 2014X, that's very similar to the new, you know, iPads and smart telephone, and you can see all the functions that you are using. You don't see the unnecessary functions that you're not using right now. But so that's, you know, I think that's a very good improvement. But to just be clear, that was not the version I used in the slides here. That was the old one, yeah.
That was the old one. That's correct. So René Steiner from Yasaki, he asked for a presentation, and the presentation will be available afterwards.
Yeah.
René also had another question. He is asking if you're applying RFLP in your department.
I'm not quite sure about that yet.
I think they are using this in the Kong is using parts of this.
Yeah, we have different projects running in parallel, so
yep.
There's one part of the department that is using it, but of course the methodology is, the systems engineering methodology is something we use, but not knowing we are using it.
Yeah.
So it's just, you know, implementing the tool, then. Yeah.
Okay. I think it's fair to say it's on the way to be deployed industrially, and it's kind of a matter of time. When the right project comes up, you are kind of ready to do that in the RFLP environment. But you have projects that last for many years developing missiles. So the real projects, they have a slower pace than the students can have. So when doing this together with the students, you have a really good opportunity to play with new technology and see how it works.
Yeah, when the student, sorry?
No, and it seems to work, so you you would like to use it.
The student project is actually quite similar to a real project, so that's the reason why we are doing it, using it to test this technology.
And it's good for us because then you can communicate the results and show us something. Because when you talk about missiles, you cannot share anything.
No.
So Francis, okay, I have a question from Francis Smits. He's actually asking, is it possible to have revisions of the same file name, but with different stages of the model?
I think so. Isn't it right?
Yes, I think that's correct. We'll have you're not working in the V6 platform. You're not working with files as such, but you have models. You have models and you have revisions.
Yeah.
So the answer would be yes to that.
Yeah.
Okay. Any other question or comments from the audience? Francis says okay. Good. Is there anyone that would like to, I can unmute you if you'd like to discuss or have a direct question to, I was not able to unmute everybody, it's too many. I can unmute anyone.
And if people have questions, they can send an email or something.
They can definitely continue. They can definitely send us these questions afterwards. But I have a question from Ole Høeg here now. Do you have any experience about how the digital RFLP model in CATIA is adapted in a visual management organization?
That was not part of our work this summer, I think.
No?
No.
Visual management organization. I didn't... I could unmute Ole Høeg if you would like to explain your question or
yeah.
Ole, you are now unmuted. Can we hear you?
Hello?
Hello, Ole. What was really the question, Ole, about visual management? Or
can anyone hear me?
Yes, we can hear you, Ole.
We can hear.
Yes, you don't hear us? Ole, we hear you. We hear you, Ole.
Hello?
Hello, Ole.
Can anyone hear me?
Yes.
Yes.
Okay. I just have this question about how this digital approach in the CATIA about the RFLP model can be adapted or will match a normal organization that are more on a, I would say, a analog way of discussing matters about designing products and product structures. So if anyone have any ideas about how this is working together, the digital world and the normal way of doing business.
The analog way of sharing papers and drawing things on boards. You have a comment on that?
I think it's easier to discuss the product or how you should build up the product when you look at it visually. But of course, I'm also educated. I'm an industrial designer, so I like to sketch quite a lot in hand by myself. But you know, if you could have, for example, an iPad or a drawing tablet where you can draw straight into CATIA, for example, that would be a nice to have application. But I think it's easier to see if you draw up the product in this functional structure, then you can ensure that you are not getting any missing links, you know, that you are getting all the products or the elements in the product. I'm not sure if I answered the question right, but
well, I think that could be a challenge how to bring this information and knowledge from the digital RFLP model into, I mean, the traditional way of thinking.
Yeah, if you're meaning to printing out, okay, I'm going to show you how this is, and to print out the documentation or something, then, for example, the requirements, we can translate them into an Excel sheet.
Yeah.
So that's quite easy, and then when we translate the requirements, they are also written in different layers, so it's easy to see where the requirements belong. And then we have all the documentation in A3s. Of course, you can instead of writing A3s, you can write Word documents. Some of the students preferred Word documents because they were used to it. So some of them made a Word document and uploaded into the structure in CATIA. So then you can print it just as a regular document.
Okay. Thank you.
I think it's a valid and a very good question, Ole, and KDA also been challenging on this, how to communicate this to managers, to other people not using CATIA, and one of the answers from Dassault is actually a kind of a navigator, RFLP navigator, a cheaper, easier license that you can navigate in this structure. So you can actually not be the designer, but you can, for other people, get into this material with a different license. So it is it's in the roadmap from Dassault, but definitely the idea is to collaborate between different domains, software guys and the electronic guys, and things comes into one model. So it's a big challenge, but
yes, it's very interesting. Yes, yeah, of course.
Yeah. Because today it's a bit difficult when you're going to cooperate with people who are using another software, and and I'm a mechanical designer, and I should like to have, you know, the information from the electronic engineers and the cable designer into one, and also the logical part of it. If I'm designing a mechanical part, you know, where to put all the black boxes, you know that you're going to have a computer inside, but you don't know how big it shall be. that would be very good using the logical part of the CATIA. You can actually design a logical part in the physical model. You can, in the physical model of CATIA, before you know the detailed design, you can design a black box there representing the logical part.
Yeah, I see.
Okay, and I definitely, it is not mentioned, but all of this information, it goes into the Enovia database, so other users can kind of access the information going through Enovia or the 3D experience platform in another way. So it's about sharing.
Yeah, so the requirements, they are shared in or saved in Enovia and are linked to Enovia, the database.
Yes. Very good. That's if there are other questions, Ole, more on your mind. Otherwise, I'll mute you now.
Okay, that's fine. Thank you very much.
Thank you.
Okay.
Thank you, Ole. I think that was very good. Thank you very much, Gudrun. And if the audience have more questions, you may send them to Technia, to me, ketilomol@technia.com. I can share this email, or you can send it to, I think it was in the invitation. And we will share this information afterwards. So then, thank you very much again, Gudrun, sharing this. We're looking forward to the next steps on the model-based system engineering with you. Yeah. And so thank you very much. And to the audience, just thank you for joining today. Technia will organize more webinars coming up all the time next year. Take a look at our event calendar. On different topics, on the Enovia topics, on CATIA topics, interesting topics. If you may have some good topics you would like us to address, just give us a hint on that. So for this, just thank you again for joining, and it's time to wish you all a warm holiday season coming up soon. So then by this, we'll close this webinar. And thank to all of you.